We are using a biorepository from a previous study, the SIT study, and essentially interrogating the genome of this cohort to look for genetic markers of susceptibility to acute chest syndrome. So just to reiterate, essentially to acknowledge all the investigators on this slide, I will not be doing an acknowledgement towards the end. So we had three basic aims: to determine the role of vaso-occlusion and TLR4 signaling in acute chest syndrome. I want to show the first part of this work to highlight the work Wilbur Lam, who is a biomedical engineer. One of the objectives of the EHRA was to bring investigators who had previously not worked on sickle cell disease, to bring them into sickle cell disease for them to contribute. And Wilbur is a biomedical engineer as well as a pediatric hematologist, and he did work trying to develop this microvascular on a chip that I'll show you. Most of the work done by his postdoc, Young, who is standing next to him. This is a slightly busy slide, and so I'm just going to simply summarize. What we charged Wilbur to do was to develop sort of a microfluidic system that will allow us to study permeability of an endothelial barrier. Previous iterations of this technology had a silicone base, which allows you to look for interactions between cells, but the silicone obviously is not permeable. And so Wilbur's job was really to use an agarose-based technology that will allow him to create this microfluidic that is permeable, and it's really the first of its kind. And I can tell you that in 4 years he has been successful in doing that, and I think is actually trying to commercialize this. So schematically, this is what you see. Endothelial cells are grown in the chambers. These cells have the capacity to lay down their own basement membrane. So they are seated essentially on plastic without any coating, and they are able to lay down basement membrane and form very nice junctions, as you see from the next slide here. So here is a staining for V-cadherin. V-cadherin is the most important junctional adhesion molecule that holds endothelial cells together. And so here we are showing clearly in these nanochannels laying of endothelial cells to form an in vitro blood vessel. And this is, I believe, laminin, which is a basement membrane, protein, and collagen. So this is, contraption actually does work. And now let me see whether the video. So what a video is supposed to show is that if you have the channels without endothelial cells and you perfuse fluorescein through, the fluorescein basically diffuses throughout the channel, whereas the microfluidic that is endothelialized, you have the marker completely retained in the endothelium. This is a quantification of the data. So this is endothelialization of the channel. You can see that in the absence of endothelium, you have the fluorescent basically leak out, and then the microchannels that have been endothelialized, that really forms the barrier. This is showing a slightly different way. Now, keep in mind the timeline. So endothelial cells are seated for 14 days and there's continuous perfusion. So these cells are growing and are forming layers, cell-cell junctions, laying down basement membrane, and the flow. It's not a static mechanism. We've done a lot of experiments trying to perturb the endothelium by perfusing it with red cells from sickle cell patients, sometimes red cells with different proportions of irreversible sickle cells, to see whether or not that would disrupt the endothelial barrier. And this is basically a schematic showing that in fact that's happened. Robert's also done experiments using red cells that are infected with malaria parasites. The point of doing this was really to evaluate the barrier disrupting properties of heme. And so here's one experiment where again the endothelium and the in vitro blood vessel, if you like, is constructed on a 14-day period, right? So the cells are seated, you perfuse it, they grow, they form a very nice barrier. And here we're perfusing either 5 or 10 micromolar of purified heme for just 1 hour, washing it out. And what this does, it actually disrupts the endothelial barrier for up to 1 day. But what we didn't really expect was that this will heal. So within another 1 day, the endothelial cells basically reform the junctions. And this is not due to cells proliferating. We've done experiments to evaluate whether this is, first of all, whether this is due to cells dying and just dropping out of the barrier, or whether this is due to proliferation. It's only 1 day. It's not a lot of proliferation going on there. So essentially, heme is able to disrupt the endothelial barrier, but it's not a fatal disruption. And you can get the barrier reseal within 24 hours. This has been very useful, and what we hope to do is to take advantage of this technology to basically screen a bunch of drugs. Let me see whether this video will play. But what you see here, just to give you the summary of the data, when we perfuse these endothelialized microvessels with red cells suspension containing 2.5% of irreversible, you see beautiful flow. It flows without any problem. Whereas if you perfuse, and this was not made up, this is patient samples, and then the number of irreversible sickle cells was quantified. And so the 14.4 and 2.5 is basically what the patient had. But in this particular patient, this perfused for less than a second and was completely blocked. I think I've made this point that it has the capacity to basically self-heal. Here you're showing some micrographs of the 16 cells, with cells basically blocking the endothelium. So that's one part of the work we wanted to do, and Wilbur has delivered in creating an in vitro microvascular basically technology that allows for the first time to really quantify permeability of the endothelial barrier. There have been previous models exposing sickle cell mice to various protocols of hypoxia, 8% hypoxia or 5% hypoxia, 8% followed by reoxygenation of 4 hours. Whereas these previous models were successful in creating some sort of pulmonary inflammation, they really did not develop ACS. The mice in these models were all survived, except this 5% oxygen. Obviously, the mice die. But more importantly, even when it's 5%, if sickle cell mice are exposed to 5% and they die, and you open up the lung is really unremarkable. And so, until about 5 years ago, there really was not a murine model that will recapitulate what we see clinically with acute chest syndrome. So we developed this model, and I think it's the centerpiece of what our center was able to do. It really involves, I'm not going to go through the background, but sickle cell patients at the time of acute chest syndrome do have acute hemolysis. And so the rationale for this model was that excess heme released during that process potentially might disrupt the endothelial barrier and cause a lung inflammation. And so to model that in mice, we essentially infuse either control sickle cell mice through the lateral tail vein with purified heme. We did this experiment with live red cells as well. That does not really cause any major pulmonary complications. This is a mouse here, and one thing I always say at these talks, these mice actually do volunteer for this experiment, and they volunteer, and we tag them with a pulse oximeter. We're able to monitor their breathing all in real time. These are awake animals. They are not anesthetized. Okay, so they're just roaming around, and depending on the intervention, you can see the oxygen saturation just drop. This is showing you that using this device gives us an accurate indication of the oxygen concentration in the blood, because here you're looking at paired analysis of SpO2 and blood gases taken from the same animals, and you can see there's a very nice linear relationship. From a histologic, from a gross anatomy point of view, we don't always get this, but occasionally you get one mouse that gets a massive pulmonary hemorrhage after just being challenged with that small dose of heme that I explained. We don't get that with AS mice or with AA mice. So a modest elevation of heme causes a lethal ALI in sickle cell mice, whereas it does not in control mice. This was published some years ago in the Journal of Clinical Investigation. So just to summarize our model, if we look to the left, the parameters that one looks for in acute chest syndrome and what has been reported in patients, what we try to do with our mirror model is to try and basically see whether we can create a bench to bedside comparison. Whereas ACS etiologically is triggered by or associated with multiple factors, we just use IV heme. In terms of the presentation, it's acute. It's an acute presentation. We do see a drop in hemoglobin once we infuse heme, which is consistent with the drop in hemoglobin you see in sickle cell patients. In terms of the biology and the pathology that you see in patients, we see those also in our mice. I have to say there are not many post-mortem studies of acute chest syndrome period. I've seen probably a couple of studies. But nonetheless, edema, fat emboli, alveolar necrosis, hemorrhage, this is what has been seen in patients, and we see all of that simply by infusing heme into these mice. They develop the classical lung dysfunction of hypoxemia, hypocapnia, acidosis. We have identified that this process is TLR4 dependent. It's not just a generic effect of heme. It requires TLR4. More recently, we've shown that it requires P-selectin to an extent. And so when there's an excess of heme in the intravascular space and it gets to the pulmonary vasculature, it has the potential to cause a lethal ALI. I'm going to switch just a little bit, as we've used this model to try and understand several things about sickle cell disease. And I think this may have been mentioned yesterday, but certainly in the United States and in the West, if you look at this chart, over a 30-year period, the crude mortality in children has improved dramatically. You can see up to 67% drop in crude mortality in kids 1 to 4 years old. And part of this, as Professor Ahimfrimpo alluded to yesterday, probably is due largely to the success of newborn screening and prophylactic penicillin. If you look to the right, I don't know whether you can see it, but in that same period, the 30 years in the United States, despite the number of comprehensive studies that have been done, despite the number of centers that NIH has funded for probably up to 30 years, there has not been an improvement in the mortality of patients in the United States 20 years and above. There hasn't been any improvement in the rate of mortality. We became interested in this and tried to understand what are the major causes of death during the transition period. And this is taken from the Dallas cohort. Between 2000 to 2002 to 2010, they lost 7 kids from their cohort. If you look at the age, all of them during the transition period. A majority of these children die from acute chest syndrome, which is not surprising, because if you look at the cooperative study, and this is Vichinsky's study published in the New England Journal, kids between the ages of 0 to 9, in terms of rate of mortality, was less than 1%. Whereas in adults 20 years and older was 9%. So there's a tenfold variation between the outcome of ACS in children and in an adult. Recently, we completed a study published in the JCI Insight where we're looking at longitudinal mice, basically sickle cell mice. We followed them for a long time, trying to understand what is the basis of the deterioration of the disease process. And my time is running out, so I'm going to go really fast. Essentially, as the mice get older, the disease gets worse. And I think this was also mentioned yesterday. And here we're looking at cross-sectional data from 1 month sickle cell mice. Around 3 months, 6 months, you begin to see evidence of tissue injury in the lung. So obviously, the disease gets worse with aging. One of the things that we saw was that it appears to be correlated to heme. The capacity of sickle cell mice to degrade heme deteriorates with aging. Heme is typically degraded by an enzyme called hemoxygenase 1. Hemoxygenase 1 is regulated by a transcription factor called NRF2. And so what you're seeing here is we've created sickle cell mice that do not have NRF2 in their non-hemopoietic tissues. These mice die much faster than wild-type sickle cell mice. They have evidence of a much more impaired hemolytic disease. Their lungs get injured relatively early than sickle cell mice. Based on that, we thought, could we apply this to the transition problem that adults with sickle cell disease have? Could we take a very young mouse and give it prophylaxis to activate NRF2 to see whether that mouse at 4 months, which is an adult, would that mouse behave as a kid? And this is evidence showing that after 3 months of treatment with D3T, markers of NRF2 activation, markers of sickle cell hemolytic disease, markers of endothelial disruption are all going in the right way with respect to the NRF2 treatment. And here are 22 mice that we studied with this protocol. The mice that were given D3T prophylactically for 3 months had a survival of 7 out of 11 survived, whereas all the mice, SS mice, these are adults now, okay, these are adult mice, all of them without the protection of D3 did not survive. And you can see the SpO2 measurements telling us that in fact these mice are dying from a lethal ALI as a result of our heme infusion. I just want to spend 1 minute or two on this nanoparticle emulsion delivery agent that we're very excited about. This is a company in Tucson that developed this. Originally, this drug was developed as a contrast agent, but it's a fluorocarbon that binds oxygen and delivers oxygen at sites of hypoxia. Here we've labeled as DD1, but it's basically Novox 508. And what we found in our model is that if we give Novox 508 30 minutes, this is actually 1 hour, before heme infusion, the animals treated with the drug are able to recover oxygen saturation, whereas the saline mice are not able to do that. This is the mortality clearly showing that whereas 100% of SS mice would die without the protection of Novox 508, we're able to save 50% when we give it prophylactically. The more exciting data was actually when we gave the drug after we had induced the lung injury. In this instance, the drug actually saved 100% of the mice, which makes sense. It's very labile, and so I think what was happening is by giving it 1 hour before the challenge, most of the drug was gone anyway. But if we give it in the acute setting, it's able to rescue sickle cell mice and that have been infused with heme. These mice do not develop ALI. This is just histology showing this is a mouse that was given Novox 508. This is a treatment group, a mouse that was not. You can clearly see that Novox is able to protect these mice. Based on these exciting data, we are now planning phase 1 tox trial in Ghana, where we're going to be giving Novox to adult volunteers with sickle cell disease to see whether the drug can be well tolerated. So this is my final slide. Based on the work we've done with the UO1, we've identified multiple targets that one can develop to prevent or to treat acute chest syndrome. Hemolysis releases hemoglobin. The hemoglobin, once it's oxidized, free heme just pops out. Typically, haptoglobin is able to scavenge this, and hemopexin is able to scavenge this. But the severity of hemolysis is such that sickle cell patients don't really have a whole lot of haptoglobin or hemopexin. And so what we think is happening is that in the acute setting, and this is a new term that I'm coining, when there's vaso-occlusive hemolysis. In other words, the red cells that are trapped in small vessels, when they hemolyze, they will release heme, and if that heme gets to the pulmonary vascular bed, based on our data, it's going to cause rapid disruption of the endothelial barrier and cause ACS. TLR4 antagonist can stop this if it's given prophylactically. Hemopexin can stop it either prophylactically or as treatment. And the data I showed you, DC3, tells that NRF2 activators can stop this. More recently, we've done experiments with functional blocking P-selectin antibodies. They can also stop this to an extent. And the Novox 508, we don't know exactly how that's working, because we see evidence of edema in the mice that still survive. And so maybe if you're able to deliver oxygen regardless of the disruption of the endothelial barrier, the mice are able to survive. Given the scope of our center and what we set out to do, I think we've been reasonably successful in creating multiple models and providing novel insight into the pathogenesis of acute chest syndrome, and more importantly, identifying a new target that can then be developed to prevent or treat this dreadful lung condition. And with that, I thank you for your attention.